In automata theory, a branch of theoretical computer science, a deterministic finite automaton also known as deterministic finite state machine is a finite state machine that rejects finite strings of symbols and only produces a unique computation of the automaton for each input string. Deterministic refers to the uniqueness of the computation. In search of simplest models to capture the finite state machines, McCulloch and Pitts were among the first researchers to introduce a concept similar to finite automaton in 1943. The figure on the right illustrates a deterministic finite automaton using a state diagram. In the automaton, there are three states, S0, S1, and S2. The automaton takes a finite sequence of zeros and ones as input. For each state, there is a transition arrow leading out to a next state for both 0 and 1. Upon reading a symbol, a DFA jumps deterministically from a state to another by following the transition arrow. For example, if the automaton is currently in state S0 and current input symbol is 1, then it deterministically jumps to state S1. A DFA has a start state where computations begin, and a set of accept states which help define when a computation is successful. A DFA is defined as an abstract mathematical concept, but due to the deterministic nature of a DFA, it is implementable in hardware and software for solving various specific problems. For example, a DFA can model software that decides whether or not online user inputs such as email addresses are valid. DFAs recognize exactly the set of regular languages which are, among other things, useful for doing lexical analysis and pattern matching. DFAs can be built from non-deterministic finite automata using the powerset construction method. Formal definition: a deterministic finite automaton M is a 5-tuple consisting of a finite set of states, a finite set of input symbols called the alphabet, a transition function, a start state, a set of accept states, let W equals A1 A2, and be a string over the alphabet I pound. The automaton M accepts the string W if a sequence of states, RO, R1, Rn, exists in Q with the following conditions: RO equals QO, RE plus 1 equals I, RE, I plus 1, for I equals 0. Now 1, RNLF. In words, the first condition says that the machine starts in the start state QO. The second condition says that given each character of string W, the machine will transition from state to state according to the transition function I. The last condition says that the machine accepts W if the last input of W causes the machine to halt in one of the accepting states. Otherwise, it is said that the automaton rejects the string. The set of strings M accepts is the language recognized by M, and this language is denoted by L, M. A deterministic finite automaton without accept states and without a starting state is known as a transition system or semi-automaton. For more comprehensive introduction of the formal definition, see automata theory. Example: the following example is of a DFA-M, with a binary alphabet, which requires that the input contains an even number of zeros. M equals where Q equals S1, S2, I pound equals 0, 1, QO equals S1, F equals S1, and I is defined by the following state transition table. The state S1 represents that there has been an even number of zeros in the input so far, while S2 signifies an odd number. A 1 in the input does not change the state of the automaton. When the input ends, the state will show whether the input contained an even number of zeros or not. If the input did contain an even number of zeros, M will finish in state S1, an accepting state, so the input string will be accepted. The language recognized by M is the regular language given by the regular expression 1, 0, 0, where asterisk is the clean star. For example, 1 denotes any non-negative number of symbols 1. Closure properties: if DFAs recognize the languages that are obtained by applying an operation on the DFA recognizable languages, then DFAs are said to be closed under the operation. The DFAs are closed under the following operations: union, intersection, concatenation, negation, clean closure, reversal, init, quotient, substitution, homomorphism, Since DFAs are equivalent to non-deterministic finite automata, these closures may be proved using closure properties of NFA. Accept and generate modes. A DFA representing a regular language can be used either in an accepting mode to validate that an input string is part of the language, or in a generating mode to generate a list of all the strings in the language. In the accept mode, an input string is provided which the automaton can read in left to right, one symbol at a time. The computation begins at the start state and proceeds by reading the first symbol from the input string and following the state transition corresponding to that symbol. The system continues reading symbols and following transitions until there are no more symbols in the input, which marks the end of the computation. If after all input symbols have been processed the system is in an accept state, then we know that the input string was indeed part of the language, and it is said to be accepted, otherwise it is not part of the language and it is not accepted. The generating mode is similar except that rather than validating an input string, its goal is to produce a list of all the strings in the language. Instead of following a single transition out of each state, it follows all of them. In practice this can be accomplished by massive parallelism or through recursion. As before, the computation begins at the start state and then proceeds to follow each available transition, keeping track of which branches it took. Every time the automaton finds itself in an accept state, it knows that the sequence of branches it took forms a valid string in the language and it adds that string to the list that it is generating. If the language this automaton describes is infinite, then the computation will never halt. DFA is a transition monoid. Alternatively, a run can be seen as a sequence of compositions of transition function with itself. Given an input symbol, one may write the transition function as, using the simple trick of currying, that is, writing for all. This way, the transition function can be seen in simpler terms. It's just something that acts on a state in Q, yielding another state. One may then consider the result of function composition repeatedly applied to the various functions, and so on. Using this notion we define. Given a pair of letters, one may define a new function, by insisting that, where denotes function composition. Clearly, this process can be recursively continued. So, we have following recursive definition, where is empty string and, where and is defined for all words. Repeated function composition forms a monoid. For the transition functions, this monoid is known as the transition monoid, or sometimes the transformation semigroup. The construction can also be reversed. Given a, one can reconstruct a, and so the two descriptions are equivalent. Local automata. A local automaton is a DFA for which all edges with the same label lead to a single vertex. Local automata accept the class of local languages, those for which membership of a word in the language is determined by a sliding window of length 2 on the word. A mile graph over an alphabet A is a directed graph with vertex set A and subsets of vertices labeled start and finish. The language accepted by a mile graph is the set of directed paths from a start vertex to a finish vertex. The graph thus acts as an automaton. The class of languages accepted by mile graphs is the class of local languages. Advantages and disadvantages. DFAs were invented to model real-world finite-state machines in contrast to the concept of a Turing machine, which was too general to study properties of real-world machines. DFAs are one of the most practical models of computation, since there is a trivial linear time, constant space, online algorithm to simulate a DFA on a stream of input. Also, there are efficient algorithms to find a DFA recognizing the complement of the language recognized by a given DFA. The union intersection of the languages recognized by two given DFAs. Because DFAs can be reduced to a canonical form, there are also efficient algorithms to determine whether a DFA accepts any strings, whether a DFA accepts all strings, whether two DFAs recognize the same language, the DFA with a minimum number of states for a particular regular language. DFAs are equivalent in computing power to non-deterministic finite automata. This is because, firstly, any DFA is also an NFA, so an NFA can do what a DFA can do. Also, given an NFA, using the powerset construction one can build a DFA that recognizes the same language as the NFA, although the DFA could have exponentially larger number of states than the NFA. On the other hand, finite state automata are of strictly limited power in the languages they can recognize. Many simple languages, including any problem that requires more than constant space to solve, cannot be recognized by a DFA. The classical example of a simply described language that no DFA can recognize is bracket or Dyke language, that is, the language that consists of properly paired brackets such as Word. Intuitively, no DFA can recognize the bracket language because there is no limit to recursion, that is, one can always embed another pair of brackets inside, and hence would require an infinite number of states to recognize. Another simpler example is the language consisting of strings of the form a and bn for some finite but arbitrary number of a's, followed by an equal number of b's. See also, acyclic deterministic finite automata, monadic second-order logic, quantum finite automata, read-only right-moving Turing machines, Turing machine, two-way deterministic finite automaton, notes, A. B. Hopcroft 2001, McCulloch and Pitts, Rubin and Scott, Gowda, Prabhakar, Application of Finite Automata, A. B. Lawson pages 129, Sakharovich pages 228, Lawson pages 128, Sakharovich pages 105, Lawson pages 63, Lawson pages 46, references, Hopcroft, John E. Mitwani, Rayev. Ullman, Jeffrey D. Introduction to Automata Theory, Languages, and Computation. Addison Wesley. ISBN A0-201-44124-1. Retrieved November 19, 2012. Lawson, Mark V. Finite Automata. Chapman and Hall CRC. ISBN A1-58488-255-7. ZBLA 1086.68074. McCulloch, W.S. Pitts, E.A. Logical Calculus of the Ideas Immanent in Nervous Activity. Bulletin of Mathematical Biophysics, 541 Euro 544, Rubin, M.O. Scott, D. Finite Automata and Their Decision Problems. IBM J. Res. Develop 114 Euro 125, Sakharovich, Jack. Elements of Automata Theory. Translated from the French by Ruben Thomas. Cambridge, Cambridge University Press. ISBN A978-0-521-84425-3. ZBLA 1188.68177. Sipser, Michael. Introduction to the Theory of Computation. Boston, PWS. ISBN A0-534-94728-XA. Section 1.1 Finite Automata, ppA 31 Euro 47. Subsection Decidable Problems Concerning Regular Languages of Section 4.1 Decidable Languages, ppA 152 Euro 155.4.4 DFA can accept only regular language. External links, DFA Simulator, an open-source graphical editor and simulator of DFA.